I'm Dr. Sureka Samundi, Assistant Professor, Department of Aeronautical Engineering, Bharat Institute of Higher Education and Research. Yes. So today we will deal on the rudder requirements. In the previous session, we have come across the one engine inoperative condition. So in this session, we will see the two functions of the rudder. So one is the crosswind landing, and the other is the adverse yield. Yeah. So yes. So what is crosswind landing? So look into that figure. So you see the speed and the direction in which the wind blows can affect the airplane's ability to land. And of course, no one can predict it. And if the wind is moving perpendicular to the runway at a relatively fast speeds, then the pilot must adjust the airplane accordingly. So otherwise, what will happen? So the airplane may land in the sides of the runway. And one of the good news is that the most pilots are familiar with these landing process. Yeah, so what is crosswind landing exactly? A crosswind landing is a landing process that involves maneuvering an airplane so that it's able to land in crosswinds. So even during the crosswinds, the pilot will be able to land the aircraft safely. So that is called as the crosswind landing. So like the crosswind occurs when the wind blows perpendicular to the runway. So it is not that the wind will always blows perpendicular to the runway. It may blow in any direction. It may even blow parallel to the runway, any direction which falls between the perpendicular and the parallel of the runway. So anything like the landing process allows the pilot to safe land in the crosswind. So that is what is the crosswind landing. So yeah, so another important thing about the crosswinds is the crosswinds were more concerns for the pilot because you see it will change the angle of attack of the airplane. So and therefore it will prevent it from the landing on the runway. So it is very important that it concerns the most. The pilot should rely on the crosswind landing to safe land during these crosswinds. So crosswind landing is playing a major role. So when you just look into this figure, can you see this? The wind direction is actually perpendicular to the runway. So observe the second aircraft from the right. So there is a change in the direction, whereas the left-hand side aircrafts are just moving along the runway, all three aircrafts. Whereas suddenly, due to the crosswind effect, there is a change in the direction of the runway. But finally, look at the first aircraft in the right. So it landed on the center line of the aircraft. So this is what is actually expected. So this is done by the two methods of the crosswind landing. So the two methods are, one is the crab landing, other one is the side slip landing. Okay. Yeah. So this is the crab method. So when you see the crab method, you see crab. As the name denotes, it is about the crabs. So how do the crabs move? The crabs move sideways. So when the aircraft is about to land and when there is the crosswind, the pilot should point the nose into the wind. So when you look into this figure, what is happening? The aircraft is moving towards the wind direction. The pilot should point the nose into the wind. And when you observe the wings are actually level, right? So this is called as the crab for the drift correction. And the crab angle is maintained until just prior to the touchdown. So it is in flare condition. So the crab angle is maintained until just prior to the touchdown. And yes, another important thing is the longitudinal axis must remain parallel to the flight path. The pilot should ensure that. So just before the wheels contact the ground, that is at the moment of touchdown, the pilot should stop that drift so that the wheels are aligned with the runway. So something like this, the runway is somewhere here. It is moving in this direction. The pilot should ensure that at the moment of the touchdown, he should stop that drifting. Drifting is moving away with the wind. So he should stop the drift so that the wheels are aligned with the runway. The pilot may use the crab method. Many pilots actually adapt using this crab method. But there may be some ruptures. It may cause some ruptures in the landing gears. But still, when there is the crosswind, you don't have any other glue, right? Yeah. So this is nothing but the crab method. Okay. So crab method. In the crab method, the aircraft should point points the nose of the aircraft should point into the wind, and the wings must be level. So when you see the other side slip method, you see here the wings are level, right? Whereas in the side slip method, what happens? The wings are not level. It is rolling in the direction of the wind. So keep this in mind. So in the crab method, the aircraft should move in the direction of the wind and the wing should be level. Okay, so the pilot should manage something like this, and at the point of touchdown, the pilot should manage to maintain the aircraft along the center line of the runway. So this is nothing but the crab method. And since the aircraft drifts in the direction of the wind, it moves sideways with the wind. This method is called as the crab method. Yeah. Yes. The next method is nothing but the side slip method. You see, can you look into the figure? The aircraft is not moving in the direction of the wind. So the wind is flowing from the right, but the aircraft is not pointed towards the wind direction. And also the wings are not level. It is rolling towards the wind. And yes, the wing which is pointed, which is in the direction of the wind is called the upwind wing. Okay, the wind which is in the direction of the wind is called as the upwind wing, and the wing which is opposite to that is the downwind wing. So always keep this in mind. Upwind wing means only in this direction the wind is flowing. So that is upwind wing. So as far as this aircraft is concerned, the right wing is called as the upwind wing, and the left one is the downwind wing. So the aircraft is rolling towards the upwind wing, which means that look at this figure, the upwind wing goes down. So which means there is less lift generated than the left one. So which means the aircraft is tending to move towards the direction of the wind. Yes, so it is rolling towards the wind. So, but it should not turn right. So that is what is our intention is. It should not turn towards the direction of the wind. So, the lowering the upwind wing, like simultaneously, the pilot should apply sufficient opposite rudder. So when he is applying opposite rudder, what will happen? It will tend to move in the opposite direction. So that's it. So because of the rolling, the aircraft will tend to move towards the right, and because of the rudder deflection in the opposite direction, it will tend to yaw towards the left. So those two movements will be nullified. So this is what is actually happening during the side slip. So both will be nullified, and it will tend to keep the airplane's longitudinal axis aligned with the runway. So the drift is controlled by the aileron, and the heading is controlled by the rudder. And if the crosswind diminishes, the corrections may be reduced, of course. Yeah. So during flare, what is happening, and during touchdown, what is happening? So during the flare only, the pilot should hold the upwind wing downwards. He should ensure that he is holding the upwind wing downwards, and also he should ensure that he is maintaining the track down runway with the opposite rudder deflection. Got it? So this should be ensured in flare condition. So during touchdown, the upwind wing wheel should touch first. So when you see, this is the right wing is moving down, and the pilot should ensure that that wing's wheel is touching down first, followed by the downwind main wheel. So keep straight with the rudder. The aircraft should be kept straight with the rudder and hold full aileron into the wind. So now he should gently lower the nose wheel to the runway. And finally, he should use the brake to stop. So this is how they will land using the method of side slip during the crosswind landing. Got it? So the aircraft must be set up straight. The drift is controlled by the aileron and the heading is controlled by the rudder. So during flare, the pilot should hold the upwind wing down. So as far as this diagram is concerned, it is in the right hand side. So he should hold the upwind down, and the heading is controlled by the opposite rudder deflection. And during the touchdown, the pilot should ensure that the upwind main wheel touches first, and it is followed by the downwind main wheel. And you should keep the rudder straight and hold full aileron into the wind, and gently lower the nose wheel to the runway. Got it? So finally, he'll apply the brake to stop the aircraft. So this is what is the side slip method. So got it? So just look into this figure. So yeah. So this is all about the crosswind landing. Okay. And you see, in case of the multiple runways, the crosswind landing can be diminished predominantly, so that he will not experience that impact in case of the multiple runways. Whereas no, that is not actually practical. The pilot may even land in the single runway. So the crosswind landing will definitely be an impact. And also even during the multiple runways, you see, because of the lightweight of the aircraft and the dimension of the runway, the width of the runway, the pilot should perform the crosswind landing even in a multiple runway. Okay, so this is what is all about the crosswind landing. And also there is another method, one that is called as the decrabbing. So in decrabbing, they involve both the crosswind landing techniques, both the crab method and the side slip method. So when the pilot involves both those methods, then that corresponding method is called as the decrab method. Okay. So maintaining the wings so that they are level at all times. And the pilot will typically point the airplane's nose into the wind and allow him to safely land the airplanes in the crosswinds. So this is nothing but your decrabbing. So in decrabbing, he just involves both the methods of the crosswind landing. So that's it. So the next methodology is the adverse yaw. So adverse yaw is one of the important functions of the rudder. You see, so now look at this aircraft. So what is adverse yaw? When there is yawing moment due to the aileron deflection. Aileron will give rolling moment. So that is by nature. But when there is a yawing moment due to the deflection of the aileron, then that is called as the adverse yaw. Got it? So yaws should be controlled by the rudder, whereas here the yaws generated because of the aileron deflection. That is the reason why we call that as adverse yaw. So during rolling, one aileron will move downwards, the other will move up. So this is the aileron control, and the aileron is controlled with the control stick or the control wheels. Okay, so now when the aileron which is deflected downwards, it creates more lift. because of the high pressure distribution. So when there is high pressure distribution, obviously the lift will be more. So when there is more lift, then the lift induced drag will also be predominantly more comparatively. So when you look into this aircraft, so the right wing aircraft, it should be the wings of the aircraft is in the position of the pilot. Okay, so when you see in the position of the pilot, then the pilot's right wing. So in that wing, the aileron is reflected downwards, and the pilot's left wing is deflected upwards. So we can see that in this sketch. So now look at this lift and the drag. The arrow marks, the magnitude of the arrow marks indicates the value of the lift and the drag. So here in the right wing, the lift is higher than the left one. So which means that because of this pressure distribution, there is more lift generated. So when there is more lift generated, obviously, then the less lift generated wing will move down. So the right wing is rolling downwards. So this is actually happening. So, but you see, when there is more lift, the drag will be more, right? So when the drag is more, then definitely it will just pull the aircraft towards the direction. So since in this sketch, the right wing is having too much drag, so which means that it is dragging the aircraft that side, so which means that the aircraft will tend to yaw towards that direction. So that is nothing but your adverse yaw. Got it? Our intention is to roll towards the left. So that is why the left wing is left aileron is deflected upwards. But what actually happened? Because of the increase in the lift in the right wing, there is more drag produced, and this drag will tend the aircraft to yaw towards the direction. So because of the aileron deflection, the yaw is generated, and hence it is called as the adverse yaw. Keep that in mind. Yes. So how can we nullify this? But the pilot should roll the aircraft. But when his intention is not yawing, and when his intention is purely rolling, and because of this adverse yaw, when the aircraft yaw, like how can he recover from this? So there are 4 methods to recover from the adverse yaw condition. One is the FRISE aileron, and the next one is the differential aileron, and the spoilers, and finally the cross-coupled controls. Yes. So you see FRISE aileron. So when you see the aileron, the part which is hanging away from the airfoil, the rear part is called as the FRISE aileron, and the shape. This is not a conventional airfoil type shape. The lower part of the is completely, it is straightened. So when you see this, the first figure indicates the neutral position of the aileron, and the second one is it is deflected upwards, and the third one is it is deflected lower direction. So when you see when it is deflected upwards, what will happen? When it is deflected upwards, the air molecules are expanding, so thereby reducing the lift generation. So this actually happened in the left wing. So in the left wing only it is deflected upwards. So here it is deflected upwards. When this aileron is deflected upwards, what happened? Because some part of the aileron is just projected outwards. So because of this, there may be an increase in the profile drag. So when you look at this, so this right wing is having more induced drag. So this increment in the induced drag is nullified by the increase in the profile drag because of this type of configuration. Got it? So whereas in the previous case, what happened? Nothing happened. Like the drag is less and there the drag is more. So this increment in the drag is nullified by the change in the shape of the aileron. So when that aileron is FRISE aileron, then the FRISE aileron will be projected outwards, so thereby increasing the profile drag. So this profile which increases the drag when it is deflected in the upward direction. So this drag, this increment in the drag will be nullified by that drag, so thereby maintaining the aircraft moving along the flight path. Okay, so now look at this. When the aircraft, when the aileron is deflected downwards, so what happened? There is no change at all. So here, no, when it is deflected downwards, there is no increment in the profile drag, because that no part of the aileron is projected outwards. So it is as such, there is no change at all. So only in the downward deflection aileron, there is only increment in the profile drag. In the induced drag. Whereas when the aileron is deflected upwards, there is an increase in the profile drag. So got it? So this is what is nothing but the FRISE aileron. So adverse yaws, when an aileron is deflected downwards because of the pressure distribution, more lift will be generated. When there is more lift generation, obviously it results in the increase in the drag. So this drag will tend to turn the aircraft in its position. So because of the aileron deflection, the aircraft is turning, and hence it is called as the adverse yaw. So this can be nullified by implementing the FRISE aileron. So the shape of the FRISE aileron is such that when it is deflected upwards, it will it will be projected outwards. So thereby it creates the profile drag. So this increment in the profile drag will be nullified by the increment in the induced drag due to the aileron deflection. So thereby the drag is maintained, and the turning is controlled. Got it? So this is your FRISE aileron. And the next one is the differential aileron. So when you see in case of the differential aileron, so the aileron deflection will happen simultaneously. When one is deflected downwards, the other will move upwards. So this is happening simultaneously. But the angle of the deflection is controlled in the differential aileron. So when you look at this is actually happening simultaneously. When you see the left figure, the upward deflection, it is more, that angle of the deflection in the upward direction is more than that of the downward direction. So by varying angle of deflection, this is actually nullified. So when it is deflected downwards, there will be more induced drag generated, right, because of the pressure distribution. So look at this first figure, second figure, the right hand side figure. So here it is deflected upwards, so which means that it is projected in the air, so thereby high profile drag is created. Whereas when it is deflected downwards, this is the normal airfoil configuration. This is not the FRISE aileron configuration. So when it is deflected downwards, in addition to the induced drag, there are some little increase in the profile drag. So the summation of this induced drag and the little increase in the profile drag will be nullified by this high profile drag, which is created due to the aileron deflection upwards, like upward deflection of the aileron. So got it? So just observe this figure carefully. So when both are deflected in the equal angle only, both will have the same value of the profile drag. But when they are deflected at different angles, obviously the higher deflected angle will have more profile drag than the lower deflected aileron. So when it is deflected down during that downward deflection, the angle is less than that of the upward deflection angle. So thereby this changes in the drag can be nullified by implementing the differential aileron. And the next one is introducing spoilers. When you see the spoilers, so this is what is spoilers. Spoilers can be deflected in only one direction. It can be just the spoilers are to spoil the lift. So spoil the lift means it will be deflected in the upward direction. Downward deflection means it will increase the lift, right, due to the pressure difference. Whereas the spoilers will be deflected only in the upward direction. When you see this figure, there is no possibility of the spoilers to be deflected in the downward direction. There is a restriction, obstacle. So always keep this in mind. The spoilers can be deflected only in the upward direction. So when the spoilers are deflected in the upward direction, there will be the weight generated and thereby spoiling the lift generated. And what is our intention? So our intention is to have the less drag position. It should not roll towards the more drag deflected, more drag generated wing. So this so you see there is less lift. So this is actually the spoiler should be deflected only in this wing. Yeah, only in this wing. When the spoilers are deflected in this wing, automatically there will be the less lift will be generated. That's okay. Our intention is to roll towards the less lift generated wing direction. So no problem at all. But what is our intention? We are just concerned about the drag generated. So when the spoilers in this left wing are activated, then what will happen? Obviously, it will create more drag. So this drag will be nullified by the drag which is created due to the aileron deflection. So got it? So this is the point. So our intention is to increase the drag in the lowering wing. So when our intention is to increase the drag in the lowering wing, and so I should activate the spoilers in this wing. When I activate the spoilers in this wing, there will be more drag generated because of this profile. So this is how the spoilers act in order to compensate the drag. Got it? Yes. And finally, the cross-coupled controls. Maybe it is now in the current decades, it is like it's completely automated, fully automated aircrafts are there. So both the aileron and the rudders are cross-coupled. Can you see this diagram? Look into the right hand side sketch. This red colors are called as the interconnecting springs. So these springs are connecting the control wheels or the control stick and the pedal. Can you see this? So when the aircraft is rolled, when the aileron is rolled, automatically there will be the deflection of the rudder in the opposite direction. When the aileron rolls, the aircraft will tend to move towards the higher wind direction. So when the rudder is deflected in the opposite direction, what it happens? It will tend to turn the aircraft in the lowering wing direction. So the rolling moment and the yawing moment, which is generated by the aileron deflection will be nullified by the yawing moment which is generated by the rudder deflection. So simultaneously this will happen. So this is why what is called as the cross-coupled controls. Okay. So the rudder deflects with the aileron. So this wing. So look at this figure. So what happened to this left side wing? The left side wing moves down. So when the left side wing moves down, the aircraft will tend to yaw towards the right hand side wing. But what happened to the rudder? So the rudder is deflected in the lowering wing. So when the rudder is deflected towards the lowering wing, the aircraft tend to yaw towards the lowering wind direction. So because of the aileron, it will tend to move towards the higher wind direction. Because of the rudder deflection, it will tend to turn towards the lower wing. So thereby that yaw moment is compensated, thereby maintaining the steady condition. So this is how the adverse yaw is nullified. Got it? So I think you have some better clarity on what is crosswind landing and the adverse yaw. Yes, we will see the rest in the next class. Thank you, guys. Thank you.